Okay, so now I'm going to talk you through a brief history of solubility modelling, and just to kind of emphasise how much technology has come on over the span of time I'm talking about. For each model, I'm going to show you the most popular smartphone the year that it was released. So these models are underpinned by experimental work, and these experiments take a known melt composition, they control the temperature and the pressure, and ideally they control the fluid composition. So this might be in equilibrium with a pure water fluid, a pure CO2 fluid, or a mixed water CO2 fluid. And then the models try to relate the solubility of a given volatile, for example CO2, with these different variables. So this graph is from the seminal work of Jackie Dixon. And what she shows is that for 3 different melt compositions, a tholite up to a lucitite, as pressure increases, CO2 solubility increases, but there is a big contrast between these different melt compositions. The lucitite dissolves more than 3 times as much CO2 as the tholite. So with time, you can kind of think of the progression of solubility models a bit like this cartoon of what your paper looks like before and after peer review. In the 80s and 90s, solubility models were relatively simple. And then from the 2000s onwards, they've become progressively more complicated. So for example, they've generally become more thermodynamic, and part of this is that people now have access to computers, like in their homes, everywhere, so it's more reasonable to kind of supply a thermodynamic model, and it's easier to calibrate them as well. They've also started to include non-ideality. This means that the direct interactions between CO2 and water are considered, rather than just saying adding CO2 dilutes water and vice versa. So for example, this might be looking at how adding small amounts of water as OH- actually increases the solubility of the carbonate ion initially. As more and more experiments have been done, spanning a wider and wider range of melt compositions, in general these models include more and more complex terms accounting for the effect of melt composition on volatile solubility. And then sort of the final frontier, which is still very much being addressed, is the influence of other fluid species. All the models we consider today are just considering water and CO2, but we also need to be asking questions in future, like how does adding chlorine or sulfur change the solubility of these major volatiles? So the first model we're going to discuss today is the Dixon model. So as I briefly said in the introduction, they actually examined 5 basaltic compositions in terms of silica content, but with a range of sodium and potassium contents. And they found this very clear relationship between CO2 solubility and melt composition at a given pressure. And what they did is they saw that the amount of CO2 that dissolves is a strong function of this parameter pi in the melt. And pi is calculated from cation fractions of silica, aluminum, calcium, potassium, sodium, magnesium and iron. So you can see this relationship here shows how CO2 increases with pi at a fixed pressure and temperature. But then Jackie was examining a suite of lavas from the North Arch volcanic field, and it just so happens that in this specific field there is a very strong correlation between pi and silica content, which means instead of having to calculate this every single time, you can use silica content as a proxy for pi and therefore a proxy for how much CO2 dissolves. So what they did is they took these initial models from Dixon et al. 1995, and the amount of CO2 that dissolves as a carbonate ion and the amount of water that dissolves as molecular water is basically an equation which has a variety of fugacity terms, a variety of thermodynamic terms, so like delta V's, R over T terms, and then there was this constant, these two here. And they updated this in 1997, so instead of being a constant, this was now a function of melt composition, and specifically the silica content of the melt. So you can see here, as you progressively add SiO2, this term becomes smaller and smaller, so more silica, lower CO2 solubility. The opposite is true for water. As you add silica, more and more water dissolves. Okay, Gordonmore comes along in 1998 and measures a wider range of silica contents, and specifically was looking at water solubility up to 3 kilobars. And their model is relatively simple, has an A over T term, a term for the fugacity of the fluid and a constant. And then finally it has this summed term, and this is the term that accounts for melt composition. So basically there is a constant for aluminum, iron and sodium, and this is multiplied by the fraction of that in the melt, and then this is all multiplied by a P over T term. And it is quite interesting to see that they chose these 3 oxides, which is different to the silica that was chosen in the Dixon model of water solubility. Okay, 2002 comes along, great technological advances since 1997. We now have our first camera phone. And Sally Newman and Jake Lowenstern took the model of Jackie Dixon for basalt and coded it up in Excel. So that's what the model is for basalt. For rhyolite, it uses a variety of different bits of information from different models, so from Stoper, Fogel and Rutherford, Silver and Blank. And for water, it uses a kind of Dixon-like model with some changed coefficients. If you want a bit more detail about exactly how the rhyolite models work, I suggest you look at VESIcal 2. But this was sort of that GUI, easy to use user interface that's become incredibly popular because it was very easy to do all of these different features: saturation paths, degassing paths, isobars, etc. Okay, Liu comes along in 2005 and is specifically targeting rhyolitic melts and both water and CO2 solubility. And this model is fully empirical and it has no melt composition term because such a small range of melt compositions were examined in that predominantly rhyolitic data set. And this is kind of the first model that represents non-ideality. And we can look at that by examining isobars. So these are lines shown at the same pressure for different solubility models. And what you can see is volatile calc rhyolite and all of the older models. As you add water, the amount of CO2 that dissolves progressively goes down. You're simply effectively diluting the presence of the other species in the gas phase. Whereas in contrast, Liu, which is shown by this blue line, as you add small amounts of water, CO2 solubility actually goes up and then it starts to drop again like volatile calc rhyolite. And this non-ideality is also seen in magmaset and papale, which are more recent models we'll get to soon. And very simply, this just results from the fact that you have like P water terms in the CO2 solubility, so you can get that complex behaviour. And generally there's a lot of P terms in this model raised to varying powers, which allows it to have that complicated shape. 2006 comes along, we now have keypads on phones. And this represents kind of the first really big thermodynamic model that we have that was calibrated on a wide range of melt compositions. So you can see the task diagram here uses the calibration data set of this model. And this builds on previous papers by Papale in 1999 and 1997. Because this model is fully thermodynamic, it's a little bit harder to understand the effect of melt composition than it is with, say, the Moore or the Dixon model. So melt composition in these thermodynamic models is handled through interaction terms, and these are expressed as W and then a subscript of a volatile element and a major element. So for example, this interaction term looks at how CO2 interacts with magnesium in the melt. Their interaction terms for CO2 consist of 2 constants, the second of which is multiplied by this ln P over P naught term, where P naught is a reference pressure. And what this basically means is the effective melt composition is not constant across pressure space. Depending on the sign of the W0 and the W1 coefficient, it may be that progressively adding one oxide causes, say, CO2 solubility to go up at a certain pressure, and the same change may cause solubility to go down at a different pressure. Water has only a single term and no pressure sensitivity. So we can look at the coefficients. They are shown in white here. And then the error on the coefficients is shown to the right hand side, and these are coloured, so less than 10% is green, up to 25% is sort of salmon, and then higher than 25% is red. What you can see is that for water, the errors on these coefficients are really quite small. And this is also supportive of the fact that Papale show there is no noticeable change in water coefficients between the 2006 calibration and the calibration they do in 1999 using a considerably smaller calibration data set. And this basically shows water solubility is well constrained. As we add more and more experiments, we're not getting a different result. That was not true for CO2. They noticed big changes in coefficients. And you can see even with this much larger calibration data set in 2006, there are large errors on these coefficients. So for example, the error on the FeO W1 coefficient is 1,500%. The other thing you'll notice is that this model incorporates Fe2O3 and FeO species, and this means it is highly sensitive to the melt redox that you tell it your melt has, or the exact proportion of FeO to Fe2O3. What's really interesting is if you look at the size of this Fe2O3 component, it is absolutely massive compared to all of the other components. And the FeO component has very, very large errors. I'm not going to go into this in detail, but if you're interested in this sensitivity to redox, and we talk about how this is likely spurious, I would recommend you to look at the VESIcal 2 paper for more detail. 2012, ixon and Marziano come and do a great service to anyone sort of working in this region of compositional space. Far, far more experiments on basalts up to higher pressures than we had previously. And this model is fully empirical. Again, you have a term for water, and then you have all of these different constants multiplied by different melt parameters. So for example, the constant DAI is multiplied by the AI index, which is basically the fraction of Al2O3 over calcium, potassium and sodium. Similarly, there's these two terms, which is the sum of iron and magnesium times by a constant, and the sum of sodium and potassium times by a constant. And then finally, the final melt composition term is this Nb over O term, and this basically incorporates almost all of your oxide species. So this model is strongly sensitive to melt composition. For water, slightly less terms, the only melt composition term is this Nb over O term, which is the same as that above. 2014, Shishkina cover even more of this sort of alkaline basalt space. And they also produce an empirical model, but this is very simple compared to that ixon and Marziano model. The concentration of CO2 dissolved in the melt is simply a constant times by the ln of the pressure, minus another constant, and then a third constant times by pi star. And pi star is pretty similar to the original pi value of Dixon, but instead of attaching negative coefficients to silica and aluminum, it divides through by the fraction of these instead. For water, there are a variety of p squared, p cubed terms, and this gives it a complex shape. And then the only effective melt composition is in terms of the sodium and the potassium content of the melt. 2015, as all of these experiments have progressively been done, the overall calibration dataset has continued to expand, and Mark and Gwill compile this and make a new thermodynamic model. This is pretty similar to how Papale works in that it has these W terms, which describes the interaction of the volatile with the melt. What you'll notice is while Papale just had a CO2 term, this model actually considers the speciation of carbon. So it has a CaCO3 term, which looks at the solubility of the carbonate ion, and that's what's going to dominate in basalts. And then it has another term for the solubility of molecular CO2. And that is going to be what is dominating in your rhyolites. And you can see compared to Papale, the errors are significantly smaller, particularly on these CO2 terms. So now this is when we're going to pass on to the first demo of how VESIcal is actually working using single sample calculations.